Are we on? Great. Okay. So, oh wait, I forgot my glasses. Just a sec. Okay. So where were we? Ah, yes, right. Welcome to Rocket Engine Development, Design, Part 1.5, where I get equations and hopefully have a better... Gosh darn it. Gosh darn it, the stream's already screwing up again. Oh well. So, today, I'm going to be trying to get at actual equations. I won't be able to solve them. That is for an No, that's for the next video where it should hopefully be Rocket Engine Design Part 1.75. Because overall, this is a weird little story arc. Oh, how I hate my computer, it's so slow. Anyway, so, this page, which is in the description currently, literally right here, I really do not like this. Anyway, so, which is in the description of the live stream, is this page right here. This is Rocket in Space Technology by broinig.us/space/propose.htm. There's no L in there, I don't know why. Okay, so for this, I'll be trying to figure out what equations I'm going to need to design this. Now mind you, because of this, being a full flow staged combustion cycle, there's fuel and oxidizer. The fuel goes in with the oxidizer, gets burnt in a pre-burner, and gets sent down to the main combustion chamber. The oxidizer does the same, but it actually has a more oxygen-rich mixture. Meaning that technically this should be burning hotter, this should be burning colder if I understand this correctly. Mind you, I'm not a rocket scientist. But the first thing I'm going to need to know is how to calculate the actual volume of the combustion chamber because of a few things. But I'm not going to worry about that right now. So, this is thrust. This can be applied to literally every part of the rocket engine, from the combustion chamber to the pre-burners. The problem with the pre-burners is how they have to work with turbines and pumps, but shouldn't be hard to do. Okay, so this is the thrust. Thrust is equal to the the rate of ejected mass flow rate. PA is ambient pressure, PE is pressure of the exhaust, VE is the velocity of the exhaust, AE is the, what is that? Oh yeah, right. It is called the area of the exit. Okay, good. This is one thing that I'll be writing down. By the way, next week, I should hopefully be getting the next actual video out, because these live streams never pan out too well. I can tell by OBS Studio telling me it goes from green to yellow to orange, red all over again. Okay, so with that, we also need a couple other equations. All of these here are mainly about useful for the burn time, but right now we're just looking at pure thrust of the overall engine. This is C. It is effective exhaust velocity, which is basically how useful that exhaust velocity is. That's why it's called effective. Impulse and momentum. This isn't really useful for us right now. What is useful is this is definitely useful. This is impulse thrust. This is VE. Ideal exhaust velocity is how fast we should accelerate the gases by the end of the whole burn to get the maximum, overall thrust. This plays in perfectly with the rest of the equation. Okay. Okay, specific heat ratio. I think we'll find that out sooner or later. Varies depending on the composition temperature of exhaust gases, but is usually about 1.2. Okay. R star is the universal gas constant. That's interesting. TC combustion temperature, average molecular weight. That's beside the point. The thing about this is we need that equation to find how fast the exhaust velocity should be going. We need this equation to find the ISP, which is useful for, which one is this? Which is useful for, I can't find it yet. Yeah, I'll find out when it's useful. So C star is actually rather important because it's just a different form of ISP. It's a different form of ISP, which is actually rather useful considering it's kind of how fast the exhaust velocity actually basically is. Okay. We'll be needing this, which is area throat nozzle, which we'll be needing these for. We'll be needing the number. We'll also be needing the nozzle exit area. This will be like really useful because it'll help us decide how big our nozzle has to be for multiple environments, such as space, the sea level, I don't know, underwater. Okay, so this I believe is, if I remember correctly. Yeah, it is. It is. I'd explain it in a later video. This is the combustion chamber. These are one of the slightly more important ones because it helps us decide like how big the combustion chamber actually has to be to combust it properly. Just because these are here doesn't mean these are all for cylindrical. These are all for cylindrical combustion chambers, but we're going to be using spherical. Because why the heck not? Thrust diameter, also going to be useful. Injector. We're going to be using I think either a coaxial swirl or pintle injector. Now, I also found this question on like how length of pipe like slows things down or causes the flow rate. I found this. You might need that for everything else. I'm also going to need to know how to calculate the volume of a sphere. I'm going to have to calculate half of it. Using that half, I will then add that with the half volume of this ellipsoid, which will be the second part, because according to Rockets by Justin, which I linked down in the description, I had a DM conversation with him once, and he said that the biggest problem with combusting it efficiently is contraction angle. So the easiest way to fix that is basically make it longer. Obviously, that's where the ellipsoid comes in, because why not? So I'll be taking half of this ellipsoid, I'll be adding it to the half of this volume, the sphere. Then I will just be figuring it out from there. Now, I'm going to start off with the main combustion chamber and then work my way up, because I feel as though finding the maximum thrust I can get from a combustion chamber, from the main combustion chamber and nozzle, is more important than the actual pre-burners right now. And then we can just use the combustion chamber as like a standard, which we will need to get from the pre-burners. But yeah. So next week, I will be taking all these equations, I will be solving them for 5 kilograms. I'm not sure how big this engine should be actually. This will be a test engine, and then I'll be scaling it up for like actual engines. So I'll be figuring out the test engine, and then the four engines which I discussed, the 2 hydrogen-powered ones, and the 2 methalox, and the 2 hydroloxes. Each of them have a vacuum version, each of them has a sea level version. I intend to fix that with an aerospike sooner or later, but for all intents and purposes, this is what we're going to be doing for the next week. I also hope to get a intro. I hope to get an intro And sorry if the live stream quality is really bad. It just, my computer's slow. Like, for example, this live stream itself is taking up 30-ish%, and it's only at anyway. So I guess I'll see you guys next week, where I hope I finally get some decent audio and yeah, decent audio, intro. I start doing that. I start using Tinkercad. Tinkercad is a very simple 3D modeling software, which I'm quite familiar with, because why the heck not? And yeah,